Okay. So today we are going to discuss this open circuit test and short circuit test, which is performed on a single phase transformer to determine the parameters of the equivalent circuit experimentally, the voltage regulation and the efficiency. Okay. So voltage regulation I have already discussed, and efficiency calculation also I have already discussed. So here we will focus mainly on how to determine the equivalent circuit parameters of a transformer by performing these two tests. Okay. Then we will discuss how to calculate voltage regulation and efficiency from these data. Okay. So first, open circuit or no load test. So open circuit test is also known as no load test because here the transformer is run at no load condition. That means the open circuit, that means the high voltage side is normally kept open, or we can connect one voltmeter if we want to know the turns ratio of the transformer. Okay. So here open circuit test is performed on low voltage side. See, this is the low voltage side and this is the high voltage side. So this is the circuit diagram to perform open circuit test. So open circuit test is performed on high voltage side. What is the meaning of this statement? Anyone, can you tell me? You have performed this experiment in basic electrical laboratory, as well as you have gone through this theoretical part also in basic electrical course, theory course. So do you know why this, what is this statement, what is the meaning of this statement? Open circuit test is performed on the low voltage
All
side.
measurements are taken with reference to low voltage side.
Anything else?
Means, sir, all the parameter go to the secondary side to primary. All the parameter will refer to.
No. That is not exactly the meaning of this statement. That is the result actually. Since we are performing the open circuit test on the low voltage side, so all the quantities which we have determined from this test are considered as referred to the low voltage side. Okay, so that is actually a result.
So readings can be easily taken with lower rated devices due to low voltage side from low
No, I am
voltage.
not asking about the reason why we perform the open circuit test on the low voltage side. I am asking about the meaning of this statement. What is the meaning? As I have said that open circuit test is performed on the low voltage side. What is the meaning of this statement? What we are going to do, or what we have done, so that we can say this?
We have to remove resistance from the low voltage.
No load connected.
Sorry, repeat.
Sir, open circuit means no load connected.
Oh
Yes,
no. No. You are not getting my question. Here you can see the it is said that the open circuit test is performed on the low voltage side, not on the high voltage side. Okay. There are some reasons behind that. I am not saying that thing right now. I am saying that what is the meaning of this? Okay. The meaning of this statement is that we are performing this test, that means open circuit test on the low voltage side, because I mean, why we are saying this? Because all the measuring devices and the supply voltage all are connected to the low voltage side. That is the reason we are saying that this test is performed on the low voltage side. Okay, all the measuring devices and the supply voltage all are connected to the low voltage side. That is why we are saying that this test is performed on the low voltage side. Okay. While we will be performing short circuit test, all the measuring devices and the supply system will be connected to the high voltage side, and in that case we will say that short circuit test is performed on the high voltage side. Is it clear now?
Yes, sir. Sir, please repeat again.
You can see this ammeter, wattmeter, voltmeter and the supply system all are connected to the low voltage winding. That means the low voltage side. While performing this open circuit test. So that is why we can say that the open circuit test is performed on the low voltage side. Okay. Similarly, while we will be performing this short circuit test, all these measuring devices and the supply system will be connected to this high voltage side only. Okay, we will change the side. In that case, we will say that short circuit test is performed on the high voltage side. Okay, is it clear?
Yes, sir.
Now the question is why this open circuit test is performed on the low voltage side and short circuit test is performed on the high voltage side. Why is it so? We can connect all these devices to the high voltage side and the supply system to the high voltage side to perform open circuit test, and the vice versa. That means we can connect all the devices, measuring devices to the low voltage side and supply system to the low voltage side to perform short circuit test. But normally it is not done. Why is it so? That is the next question. Anyone?
Sir,
Have you any idea?
yes, sir. Sir, when the devices
Yes.
are connected, the high voltage side is not open circuit anymore.
No. It is
Sir,
not like that.
sir, I guess in the low voltage side, like to obtain the flux that we need to perform the test, it is sufficient. Like, and that is the reason we don't go to the high voltage side.
No. Anyone else want to say something other than this? Okay, I will answer this question at the end of this topic. So you can uh, you can note some points while I will be discussing this test to understand this answer of this question. Okay, I will mention which point to be noted. Okay, so in open circuit test, let us discuss this thing first. So in open circuit test, all the measuring devices, voltmeter, ammeter, wattmeter and the supply system are connected to the low voltage side and the high voltage side is kept open. Okay. And then rated frequency voltage is applied to the primary side, that means the low voltage side, by using an auto transformer. So what is this auto transformer? Auto transformer is nothing but a variable output transformer. That means by changing this wiper position, we can have different values of output voltage. Suppose when the wiper position at this point, then the output voltage will be low. When the wiper position is at this position, we will have a higher voltage output. Okay, so to get our desired output voltage, we can use this auto transformer. Some fixed input is given here and we will get variable output voltage. So that is an auto transformer. Okay, normally we call it variac. Okay, variable AC output. So by using this auto transformer, we can give variable output to this transformer. So here this is the arrangement for this experiment. That means all the measuring devices, ammeter, wattmeter, voltmeter, all are connected to this low voltage side, and rated frequency voltage. Rated frequency voltage, suppose the ratings of this transformer is 10 kVA 200 volt by 2000 volt. So note this rating, please. We will be requiring this rating while discussing the answer to the questions that why this no voltage open circuit test and short circuit test are performed on the low voltage side and high voltage side respectively. Okay, so here rated voltage means we have to apply 200 volt at rated frequency, which is 50 hertz in our country. Okay, so rated voltage is applied by using this auto transformer to the low voltage side. Okay, then what happens? This voltmeter will read 200 volt, that is the rated voltage. For we have assumed that transformer as 10 kVA, 200 volt by 2000 volt. Okay, so while we are giving that input to this low voltage side, this voltmeter will record that voltage reading. Okay, now next is what will be the reading of this ammeter. Since the secondary side or the high voltage side is open circuited, that means no load is connected. That means this ammeter will read only the exciting current, which is also known as the no load current. Okay, so only exciting current IE will be recorded by this ammeter. Is it clear?
Yes, sir.
Yes, sir.
Voltmeter will read the input voltage, which is the rated voltage to the low voltage side, and ammeter will read the exciting current or no load current. Okay, now what will be the reading of this wattmeter? Wattmeter normally reads power. Okay, so no load is connected across this secondary side, so there will be no reading due to power consumption by load. Yes. Okay, then what will be the reading of this wattmeter? So when voltage is applied to this transformer, there will be some core loss and there will be some ohmic loss in the low voltage winding only. There will be no ohmic loss, that is PCU, that means copper loss, in the secondary winding, because no load is connected, so no current is flowing in the secondary winding. So only a small amount of copper loss in the low voltage winding and the core loss. This will be the reading of this wattmeter. Okay, now this copper loss will be due to the exciting current only, which is about 2 to 6% of rated primary current. Okay, so we have assumed the rating of this transformer is 10 kVA, 200 volt by 2000 volt. Okay, so what will be the primary current? Primary current is 10,000 divided by 200. So how much is this? 50 ampere, right?
50 ampere.
Yes, sir.
Right. So
Yes,
what is
sir.
the
Yes,
what
sir.
is the value of 2% of this current?
1 ampere.
2% is 1 ampere, right? Is it? Yes. So
Yes,
1
sir.
ampere.
Yes.
So this transformer is designed to flow a 50 ampere of current, but now it is only 1 ampere is flowing, which is recorded by this ammeter. So due to this 1 ampere, the copper loss will be very small, isn't it?
Yes, sir. Yes, sir.
So in comparison with this core loss, which is the rated core loss, why the rated core loss? Because core loss is voltage dependent loss and we are applying rated voltage. So this is rated core loss. Okay, so core loss is rated core loss, that is rated, and copper loss only due to this exciting current, which is a very small current. So copper loss can be neglected. Negligible amount of copper loss. So we can assume that this wattmeter reading is only the core loss, right? Can we consider it? Agreed?
So can you please repeat the last statement?
See, we are applying rated voltage and core loss is voltage dependent loss. So whatever may be the core loss here, that is the rated core loss.
Yes, sir.
Okay. And copper loss is due to only the exciting current, which is a very small current because it is only the 2 to 6% of rated current. Okay. So due to that small amount of current, the copper loss will also be very small. Therefore, though there is both type of losses are present, but we will assume that this wattmeter is reading only the core loss because
Core loss.
this copper, yes, core loss, because this copper loss is negligible with respect to this rated core loss.
Yes, agreed.
Okay, so we have 3 readings. So what are those readings? And one more thing is there, that is this, since this current is very small, so the primary leakage reactance R1 plus JX1, due to this leakage reactance, the voltage drop, that is I R1 plus JX1, this voltage drop is very small. Therefore, we can assume this, the applied voltage is equal to the V1 dash, which is equal to minus of V1, right? Exciting current is very low, therefore this voltage drop is very low, therefore we can take the applied voltage, that is the voltmeter reading, is equal to V1
Yes,
dash, which is equal to minus of E1. Okay.
Yeah. Yes.
So now we have 3 readings. V1, that is the applied rated voltage on low voltage side, IE exciting current or no load current, and PC, that is core loss. So these are the 3 readings we have got from this no load test or open circuit test. So V1 dash, V1 is the applied voltage, which is equal to V1 dash or minus of V1, exciting current IE recorded by this ammeter, and PC, that is the core loss, recorded by this wattmeter. Okay, so using these 3 readings, let us see what we can calculate. So PC is equals to V1 I cos theta 0. V1 I cos theta 0. That means the core loss is equal to voltage into IC. We know this equation, PC equals to V1 dash into IC, that is core loss component of exciting current, PC is core loss, and V1 dash is the voltage appeared across the primary winding, which is opposite to that of E1 dash. Okay,
Yes.
so using this formula we can calculate the core loss. Now using this equation we can now we can calculate this core loss. Now V1 dash here is considered as V1, and IC, recall that IC is equal to
IE cos
IE
theta.
cos theta 0, where this theta 0 is the no load power factor angle. So cos theta 0 is no load power factor angle. So we can write V1 IE cos theta 0. So in this equation, IE, V1, PC, all are known quantities because we have measured all these things. Okay, so we can calculate cos theta 0. So no load power factor cos theta 0 is equal to PC by V1 IE. Is it clear?
Yes, sir. Yes, sir.
Now from this we can draw the phasor diagram. This is the phasor diagram. Here V1 is equal to V1 dash is equal to minus of V1. So that is the applied voltage. So this is the applied voltage. IE is the exciting current which leads the flux by an angle of alpha. Voltage between this exciting current and the angle between this applied voltage and the no load current is theta 0. So this angle is theta 0, which is known as the no load component. If we resolve IE into two components, one is IC, that is the core loss component in phase with V1, another is IM, which is in phase with phi m. Okay, so cos theta 0 we have calculated. From this we can calculate IM. So IM is sine component of IE. So from that we can calculate IC and IM. IC is core loss component, IM is magnetizing component. So we can calculate IC and IM using this equation. Is it clear?
Yes, sir.
So once we get these currents, we will be able to calculate the equivalent circuit parameters RC and XM. Okay, so RC is V1 by IC and XM is V1 by IM. So core loss resistance RCL is equal to V1 by IC. Magnetizing reactance XM is equals to V1 by IM. Now normally we denote core loss resistance by RC only, but here L is used to denote that these quantities are measured from low voltage side, so they are referred to low voltage side. So these are low voltage side parameter, that is why this L is used. Okay. So the subscript L with RC and XM is used merely to emphasize that these values are for the low voltage side. I have already mentioned. So from open circuit test we have got two parameters, that is the shunt branch parameters RCL and XML. These two are equivalent circuit parameters. Any question up to this?
No, sir.
Okay. So sometimes, as I have mentioned earlier, a voltmeter is connected here. A voltmeter is connected here. So connecting a voltmeter is equivalent to open circuit. So that satisfies this condition. That is, we have to keep this high voltage side open. So this voltmeter reading and this voltmeter reading, this will give you the ratio of this transformer, that is trans ratio N1 by N2 is equal to V1 by V2. Okay. If the transformer trans ratio is not mentioned in the nameplate data, then we can use this voltmeter and this voltmeter readings to know the trans ratio. Okay. So therefore we can conclude that open circuit test gives us the following information. First of all, core loss at rated voltage and frequency, the shunt branch parameters. See, this is the equivalent circuit which we have obtained from open circuit test only. So V1 equals to V1 dash, this voltage. IE is exciting current, which is the primary current now. IE is divided here at this point into two components. One is IC, another is IM. IC is core loss component IM is magnetizing component, RC and XM, these are the shunt branch parameters of this circuit, of this equivalent circuit. So RC is core loss resistance, XM is magnetizing reactance. And also we can determine the turns ratio if it is not mentioned in the nameplate by using or by connecting a voltmeter across the high voltage winding. Okay. So if you are asked that what are the informations you will get by performing open circuit test, then you have to mention all these things, not only this RC and XM. Core loss, equivalent circuit parameters RC and XM, that is core loss resistance and magnetizing reactance, and also the turns ratio if we want. Okay.
Yes, sir.
Okay, so that's all about this open circuit test. Now let us go to this short circuit test. So here you can see all the measuring devices are connected to the. Yes.
So one doubt, sir, you had asked that question, right? Low, why we use it in the low voltage side? Sir, is it possible to calculate these things in the high voltage side as well?
Yes, yes, it is
Okay,
possible.
sir. Then yes, from this particular phenomenon, then I'm thinking that using a very low voltage on the LV side, if you are able to get this particular things informations, then why to apply a high voltage on the secondary side?
No, I'm not getting. Repeat your question.
Sir, like if we are like we are producing the same result, that is core loss, right, in this open circuit test. So compared to the higher voltage side, in the low voltage side we'll be applying low voltage, so there will be less.
See, no. That is not the question of low voltage or high voltage. That is the question of rated voltage. You have to apply rated voltage.
Yes,
so
sir.
if you want to if you want to perform this test on high voltage side, then you have to apply the rated voltage of high voltage side, which is very high normally.
Okay, sir.
As we have taken one example, 10 kVA 200 volt by 2000 volt. So you have to apply 2000 volt to the high voltage side to perform open circuit test. There are some difficulties. I will answer that question. Okay.
Okay, sir. Okay.
So short circuit test is performed on the high voltage side. As we can see from the circuit diagram that all the measuring devices are connected to high voltage side, and also the supply system is connected to the high voltage side, and the low voltage side is kept short circuited. Okay, there is a dead short circuit. Okay, so this is the arrangement. Now again we have to identify the readings of these three instruments, what they are reading. Okay, so that is the arrangement. Now how much voltage we have to apply here to perform this short circuit test? In case of low voltage side, to read rated copper loss, to read rated core loss, we had to apply rated voltage, that is 200 volt. Now what would be the applied voltage in case of this short circuit test? So see, short circuit means this is a low resistance path, or we can say no resistance path. Okay, so that means if we apply a very small voltage, then there will be a very high current. Okay, so what we can do, we can apply a very small voltage by this auto transformer, and we have to observe this ammeter reading. As we are increasing the voltage gradually, this ammeter reading will also increase. So we have to stop increasing the voltage level when this ammeter will read the rated current, I rated. Okay, so in case of open circuit test, we were applying rated voltage. In case of short circuit test, we have to apply rated current, and for that whatever may be the voltage requirement, that we have to supply. Okay, and that will vary for transformer to transformer. Normally it ranges between 2 to 12% of rated voltage of high voltage side. If the high voltage side rating here we have considered 2000 volt, so we may have to apply in between this 2 to 12% of this 2000 volt. Is it clear how much voltage we have to apply? The voltage required to circulate rated current in the high voltage side, that much voltage we have to apply, and it ranges between 2 to 12% of high voltage side voltage rating. Okay, so this now we have got two readings. So this ammeter will read rated current and voltmeter will read whatever voltage we have applied. Correct?
Yes, sir.
So normally we call this current as short circuit current, ISC, and this voltage is called short circuit voltage because we are performing short circuit test, so VSC. Now we have to identify what will be the reading of this wattmeter. Okay, let us see. See, a primary voltage, that means the voltage applied to high voltage side, ranges between 2 to 12%. Now observe this circuit diagram, equivalent circuit. This is the circuit we are going to have after performing this short circuit test and after calculation. Okay, so in this circuit, this side is short circuited. So if we apply some voltage here, what will happen? Most of the current will flow through this path. Why? Because there is a short circuited path. So a very low or almost no current will flow through this path. That means this exciting current is neglected. Okay, so total current will flow through this path. Okay, now see, there are two impedances. One is primary side leakage impedance, another is secondary side leakage impedance. This is Z1, this is Z2, and normally we consider Z1 is equal to Z2, or we can write R1 equals to R2, X1 equals to X2. Okay, so now see, we are applying 2 to 12% of rated voltage, and if these two impedances are equal, which means 1 to 6% voltage will be applied across this impedance and another 1 to 6% voltage will be applied across this impedance. Got my point?
Yes, sir.
So what happens? The thing is that half the applied voltage is appeared across this branch, which is about 1 to 6% of rated voltage. Okay, now the core loss is a voltage dependent loss, as I have mentioned in the previous case. So 1 to 6% applied voltage will produce a very small core loss. Why? Because see, 1 to 6% volt of rated voltage will produce 1 to 6% of rated flux phi. Okay, and we have seen that this core loss PC, which has two components, one is hysteresis loss, that is proportional to Bm to the power x, that is Steinmetz constant I have discussed in last class, which is having a value of ranges between 1.5 to 2.5. and the eddy current loss, that is directly proportional to Bm square. So if we take this X value as 2, we can say this core loss is approximately proportional to Bm square, correct? Eddy
Yes,
current
sir.
loss is proportional to Bm square, that is fine. Hysteresis loss is proportional to Bm to the power x, whose value lies in between 1.5 to 2.5. So if we take x equal to 2, then hysteresis loss is also proportional to Bm square. So we can say core loss is directly proportional to Bm square, approximately, right?
Yes, sir.
Yes,
So
sir.
if the flux is only 1 to 6%, then what will happen to this core loss? 0.01, that is 1%, and 0.06, that is 6%. So if you take square of this, what happens to
Very,
this core
very small,
loss?
small amount.
Very, very small.
Yeah.
So we can neglect core loss while performing short circuit test. So this wattmeter will read only which loss?
Core loss is neglected, you right? So copper loss.
Yes. So
Okay.
this wattmeter reading will read on this wattmeter will read only copper loss, right?
Yes, sir.
Is it clear to everyone? Any doubt?
So, sir, these two tests are being done to find the core loss and copper loss.
Not exactly. Not only those losses only. We are determining the equivalent circuit parameters also.
Okay.
Okay, so now we have three readings. One is ammeter reading, voltmeter reading, and wattmeter reading, and we have identified what those parameters are. Okay, so let us go to our calculation part. So VSC, that is the voltmeter reading, which is the required voltage to circulate rated current. ISC, that is the short circuit current, which is the rated current in the secondary in the high voltage side, and PSC, that is the wattmeter reading, which is the copper loss, rated copper loss, or copper loss at rated current. Okay, so these are the three readings. Now calculation. So ZEH, see, these parameters are calculated from high voltage side, that is why this H subscript is used. So ZEH is equal to VSC by ISC. What is this ZE? ZE is total impedance or equivalent impedance of this transformer referred to high voltage side. Okay. So ZEH we can calculate using this equation. Then using the copper loss and ISC, we can calculate the equivalent resistance. REH is equal to PSC by ISC square, because PCU is basically I square R loss. So using this equation or formula, we can calculate REH is equal to PSC by ISC square. So once we get REH, we can calculate XEH by this formula. XEH is equals to root under ZEH whole square minus REH whole square. Okay.
Yes,
Clear?
sir. Yes, yes.
So now see, though we are drawing this equivalent circuit like this, that means two separate winding resistances are shown, two separate leakage reactances are shown, but we have got only the equivalent resistance and equivalent reactance. So if we want to separate them for low voltage winding and high voltage winding part, then how to separate them? Actually, there is no fixed method to separate these parameters. We assume that they are equal, so simply we divide them. So R1 equals to R2 equals to half of RE, and X1 equals to X2 equals to half of XC. Clear? and that is valid for a 50 Hz transformer. If the transformer operates for higher frequencies, then this x1 and x2 value will not be equal. So that is not required here. So we are assuming that this winding resistances are equal and leakage reactances are also equal. So we can simply divide this Re by 2 to get R1 and R2 and 2 and XC by 2 to get X1 and X2. Okay, clear?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So now let us conclude. What are the informations we are getting from this test, short circuit test? Ohmic loss at rated current and frequency. So what was it while performing open circuit test? Core loss at rated voltage and frequency. See the differences. Okay. The equivalent circuit resistance and equivalent leakage reactance. For open circuit test, it was RC and XM. Here we are getting RE and XE. Okay. Now we can also determine voltage regulation as well as transformer efficiency from the open circuit test and short circuit test data. Okay. So voltage regulation, for voltage regulation calculation we need only short circuit test data, because RE and XE we require that two parameters, and the rated current value. Okay. E2 we will get from nameplate data, so we will be able to calculate this per unit resistance and reactance. And now if the load power factor is given, we will be able to calculate this voltage regulation. Okay. Now data of both open circuit and short circuit test is necessary to calculate the efficiency of the transformer as well as the parameters of the equivalent circuit. Okay. Here, while calculating the equivalent circuit parameters, we will require both open circuit test and short circuit test data, and for calculating transformer efficiency also we require both data, because from open circuit test we will get the core loss, from short circuit test we will get copper loss. Using these two losses we will be able to calculate the input power, and then we will be able to calculate transformer efficiency. Okay, that I will discuss once again. So any question up to this?
No, sir.
No, sir.
Yeah, clear.
Okay, then note down this problem. You try to solve it by yourself first, then I will discuss in next class. Take a snapshot. Done?
Yes, sir.
Okay. Today up to
So
this.
that 105 watts is that wattmeter reading.
Yes.